Hello, welcome to this MEI M1 online revision video where we're going to be looking at January 2010 question 7. This is one of the longer questions towards the end of the paper. So let's have a quick read through the question first. We've got a graph which has a specific curve which is being given to us. And we can see that for 0 to 20, this is mapping out the trajectory or the path of a small stone which is projected from a point Q. And y is the vertical distance above the ground and x is the horizontal displacement. The stone hits the ground here at some point R, and we've got to find out various things about the path of this stone. So we've got to write down first of all the height of Q above the ground, that's where it starts from. We've got to find the horizontal distance from the origin to the highest point of the trajectory, which would be around here, and show that this is 1.5625 metres above the ground. We've then got to show that the time taken for the stone to fall from its highest point there to the ground is just over half a second, 0.565. We then have to show that the horizontal component of the velocity is 22.1 and use this to work out the time of flight from Q, where the ball is thrown, to R. Finally, we have to work out the speed at which the stone hits the ground. So there's quite a lot to do in this question. It's quite a long question. So let's get started with part 1. It's a 1-mark question. Anything that says write down indicates it's pretty straightforward. Now we know that over this distance here, 0 is the starting point, and so if we put x equals 0 into here, it will give us the vertical height at point Q. So it's just a case of putting x equal to 0. Y will then be 1 over 100, 100 plus 0 minus 0. And so we get an answer of 1 metre. We now have to find the horizontal distance from the origin to the highest point of the trajectory and show that this is a particular height. There are two ways to do this. You could use calculus, differentiate this equation of this curve, and put it equal to 0, because at the maximum point here the gradient will be 0. And you can then work out the x-coordinate and the corresponding y-coordinate. However, there is a slightly easier way using the symmetry of the graph, because we can see that this is a quadratic, and because it's a quadratic it's symmetrical. And so the maximum point here will be halfway between -5 and 20. So by symmetry, the point that we're after, which we'll call x, is -5 plus 20 halved, and that works out to be 7.5. So looking at the curve, that means that this is 7.5 metres along from the origin, and we also have to work out the y-coordinate. Well, all you need to do there is substitute it into the equation of the curve. So it's 1 over 100, and if we look back, 100 plus 15x minus x squared. 100 plus 15x minus x squared. And if you work that out, it does indeed work out to be 1.5625 metres. So that's part 2, and that's 5 marks. We now have to show the time taken for the stone to fall from its highest point to the ground. So let's think about the vertical motion. If we go back and look at the diagram, from this highest point to the ground, the particle or the stone is being acted on by gravity, and we know that that is 9.8 metres per second squared. We know from the previous question that it starts from a height of 1.5625 above the ground. We need to know the time it takes to fall to the ground, so that's the thing that we're after. And then the other thing that we know is that at this maximum point, vertically the speed will instantaneously be 0. And so because we're using that as our starting point for the downward motion, that means that u will be 0. So we can use Suvat equations in the vertically downwards direction. SU, A and T means that we're going to be using S equals UT plus a half AT squared. Substituting in the values we've got. And simplifying, 1.5625 will be equal to 4.9t squared, and so t will be equal to the square root of 1.5625 divided by 4.9. And if you work that out, that works out to be 56469 and so on. And so to three significant figures, which is what we're asked for, it will actually be, as required, 0.565 seconds. Let's move on to part 4. This is 5 marks. We have to show the horizontal component of the velocity of the stone is 22.1, correct 3SF, and then deduce the time of flight from Q to R. Well, from the maximum point of the curve to that final point R, we know that the time taken to do that phase of the motion was, from the previous part of the question, around about 0.565 seconds. So from the max point to the ground, we also know from the previous part of the question, if we just flick back to the diagram, we know that from the origin to this maximum point here was 7.5 meters. That means that this distance on the right hand side from the maximum point to the ground, that must be 12.5 meters. So we can use that to say that the horizontal displacement that we're interested in is 12.5 meters. Now what's important to note horizontally is that there's no acceleration, so this is a constant velocity horizontally, and so that velocity will be the displacement divided by the time, so use the full value that you previously obtained on your calculator, and if you type that in, that gives you 22.1359 and so on. And so rounding that off to 3SF, it does indeed give us 22.1 meters per second. So that's the first part of the question. We then have to deduce, so obviously using what we've just done, the time of flight from Q to R. Now again, just flicking back to the picture, from Q to R is a total distance of 20 meters. So we need to go 20 meters, and we know that we're going at a speed of 22.1359, the full value that you got from your calculator here. So we know the time will be the distance or displacement divided by the speed or velocity. So that will be 20 over 22.1359, and typing that in will give us 0.9035, which rounds to 0.904 to 3SF. So the time of flight from Q to R is just under 1 second. One final part complete. Part 5, we have to calculate the speed at which the stone hits the ground. Now as the stone comes towards the ground, it's going to have a horizontal component to the velocity and a vertical component. So it's going to come towards the ground with a certain velocity, and that will have a horizontal component and a vertical component. Now the horizontal component we already know, because the horizontal motion is always the same velocity in this case. We worked it out in the previous part of the question. So horizontally we know, vertically we need to find out, and then once we've got the horizontal and the vertical components, we can then use Pythagoras theorem to work out the speed. Remember, speed is the magnitude or the size of the velocity. So let's work out the vertical velocity. So again, thinking about it from that maximum point, at the maximum point of the trajectory, we know that it sets off downwards with an initial speed of 0. The acceleration is again downwards 9.8, and the distance is 1.5625, and we want to know the velocity. So using SUVAT, it looks like we need to use v squared equals u squared plus 2as. So v squared will be 0 squared plus 2 times 9.8 times 1.5625. And so v will work out to be the square root of this, which is 30.625. And so it works out to be just over 5.5. So keep that value. That's this vertical component here. And so now we can use Pythagoras theorem to work out the speed, which is sometimes written like this, the magnitude of the velocity. So using Pythagoras, it's going to be 22.1359 squared plus 5.5339 squared. Use the full values, and it works out to be 22.8172, which we can round to 22.8 meters per second to 3 significant figures. So that's quite a long question, and what we'll do now is we'll go back to the first part and we'll go through and see how the marks were allocated for this question. So let's go back to part 1. This was fairly straightforward, just substituting in x is 0, and that's a mark independent there, B1. Moving on to the next part, we use the symmetry of the graph here, so we got 1 mark for working out this method here, working out the halfway point between them, and then there's an accuracy mark for getting the final answer correct. Now in the mark scheme, what they've actually done is they've said that the whole of the horizontal distance is 25. They've halved it to get 12.5, but then taken account of the fact that the graph starts 5 meters to the left of the origin to get 7.5. We included that within our working out here by doing -5 plus 20. So we've skipped that accuracy mark, but we'd still be awarded it because we've done obviously a correct method there. So that's the first 3 marks. You then get a method mark for substituting 7.5 into the equation of the curve, and this is an E mark for explaining correctly why it's 1.5625. Moving on to part 3, we get a method mark for correctly identifying to use a SUVAT equation, an accuracy mark for substituting in the correct values, and then here an explanation mark. You really have to make sure that you've shown clearly that it does round to 0.565 to 3SF, so writing down a few more digits is important there. Going on to part 4, we had 1 mark here for the use of 12.5 as being a relevant distance that we need to work with, and then we got a method mark for dividing. We were given the answer, so this is an explanation mark, and you again need to make sure that you've shown that it does round to that 3SF. The other 2 marks are then given for correctly dividing this distance by speed, so choosing to put the correct values in the correct places, and then an accuracy mark for the final answer there. Moving on to part 5, we again get 1 method mark here for using SUVAT equations and an accuracy mark for getting down to the correct velocity. We then get a second method mark for using Pythagoras, and a final accuracy mark here for making sure that we do get the correct answer of 22.8. So that's the end of this particular question. If you wanted to look at other questions for this unit or other units, please do visit our website www.furthermaths.org.uk.